I'm Huazhe, and I'm co-chairing the session with my friend Professor Wanbo Hu. If you have a cell phone with you, you can take pictures and send on Twitter or on your social media so that you can call your friends here and watch the awesome oral. Our first speaker is Christopher 50. He's from Stanford University and is presenting restructuring vector quantization with the rotation trick. Sorry about that. Welcome.
Thank you. I think we're having a bit of Discord issue. Good. Well, cool. Thank you, everyone, for attending. My name is Christopher 50, and today I'm presenting restructuring vector quantization with a rotation trick. I want to provide a brief background about vector quantization and its application in deep learning systems, specifically vector quantized variational autoencoders. Vector quantized variational autoencoders, or VQVAEs for short, are just like regular autoencoders or variational autoencoders. However, rather than having a continuous sort of bottleneck representation, they instead quantize that representation into a set of discrete tokens. So let's say we have a classic 256 by 256 by three-dimensional image. And let's say we're projecting down to a 3 by 3 by 12-dimensional bottleneck representation. We're going to apply vector quantization on each of those 9 different vectors, 9 different 12-dimensional vectors, to quantize them to a discrete token. And when I say quantize to a discrete token, what I really mean is we have a set of codebook vectors, which is basically a set of discrete vectors where you select the size of that ahead of time. So if you set 124 different discrete tokens, you take the continuous vector and you basically look up in your codebook the nearest discrete token, and then you just replace it. And then once you replace every single vector, you send that through the decoder, and that's vector quantized variational autoencoder. You should try and reconstruct the original image. And now you might expect me to talk about some information theory, maybe different loss functions, VQ GANs, sort of the typical route that one would take in this presentation, but I'm not going to do that. I sort of want to pull you along for the journey of discovery and the journey of research that we ourselves underwent when we were sort of developing this work. And that journey starts with circles and squares. So why circles and squares? Well, we really liked this one paper in ICLR last year called Finite Scalar Quantization. And they had this really cool idea that rather than learning this codebook, rather than learning these 1024, 2048, like however many have you discrete vectors, they said, hey, let's not learn these. Let's instead fix these to the vertices of a square or the vertices of a hypercube in high dimensions. And our whole idea was, hey, this is great. Rather than using like a square, let's use a circle instead. And we're going to like put these points on a circle. And that's where this publication was really heading until it didn't work so well. So our whole idea was, okay, squares are bad, circles are good. We can do this thing called spherical codes, which is actually like this really cool unsolved problem in mathematics, where you try to place endpoints on a d-dimensional sphere such that the minimum distance between any 2 points is maximized. And we're like, okay, this is going to be great. We're going to go from a square to a circle. Hopefully the reviewers will like this. It's really cool. We have some like cool coding maths. It's going to be a great publication. And in sort of exploring all of these different sort of geometries of the codebook, we really came to this combination vector quantization, which is how you get the gradient around the vector quantization operation. So vector quantization is an argmax operation. You're basically searching through the codebook and you're selecting the nearest codebook vector to your continuous vector. And that's a non-differentiable layer. If you move the continuous vector around a little bit, chances are it will be mapped to the same discrete token. So formally, the gradient or the gradient is 0 almost everywhere, and then it's undefined at the boundary. So in vector quantized variational autoencoders and these sorts of systems, you really have to ask yourself, how do you get the gradient from the quantized vector back to the encoder output? And we'll call the quantized vector Q here, and the encoder output E. So very simply, the vector quantization function maps E to Q, and that's the quantization. And we're denoting the gradient here by the red arrow. And very, very simply, how do you get the red arrow from point Q to point E? The way you typically do this is you just copy and paste it, or you apply a translation. So if we're sort of translating around the circle, you maintain the direction of the gradient as it moves from Q to E. But this kind of looks weird. So if you've taken differential geometry or maybe a course in physics, you might kind of like look at this and you might tilt your head a little bit and you're like, wait, I thought for arrows going around a circle, they kind of rotate. So perhaps the vectors that are in the tangent plane should remain in the tangent plane, and the vectors that are in the cotangent plane or that are orthogonal to the surface should remain orthogonal as it's being transported around the surface. And that looks like this. And this seems to be a much more sort of intuitive way to move vectors along sort of curved surfaces or curved manifolds. And this is because the basis vectors on curved surfaces actually change. So in 3D Cartesian coordinates, or really any sort of Cartesian coordinate system, the coordinates are flat in a sense, so the basis vectors are the same at every single point. But for other surfaces, those basis vectors actually rotate because your coordinates are, they're not flat. They're not in this like rectangular configuration. So when you actually parallel transport a vector, when you move a vector on a surface, you actually want to keep it constant. You might want to keep it constant with respect to how the basis vectors are changing, and we call this parallel transport. And that's really what we did here. So we kind of moved away from this notion of all the vectors are now on a surface to now we're transporting this vector with parallel transport. So like Levi-Cavita, Christoffel symbols, covariant derivatives. And we're really trying to move the gradient from like point A to point B in this coordinate system. And what that reduces to is basically preserving the angle. So if there's one thing that I can have you take away from this talk is what we're fundamentally doing here, and sort of the whole impetus behind the paper, is you're preserving the angle between the gradient and Q as it's transported to the encoder, versus the straight-through estimator, which is what has been done before and what has been done since for the last like 5-6 years. You sort of just preserve the direction during that transport. And now this is where you ask, like, okay, you just added a lot of complexity to this. Why are we doing this? Cartesian coordinates are amazing. We live in Cartesian coordinates. It's really nice. Why in the world would you like add all this complexity? You just said there's like no mathematical like a priori reason for like moving the gradient from like point Q to point E. Why are we doing this? What does it give us? And that's a great question, because there's no one right way to move a vector along a circle. You can just sort of define criteria and then like have that transport that satisfies that criteria. And this is where we're coming back to information theory, and where this talk sort of merges into the natural flow of a compression paper talk or a vector quantized variational autoencoder talk. And to sort of motivate this, we really want to think about this one case where you sort of have a bad fit. So if you have a continuous vector and you're quantizing to a codebook vector, if that distance is very, very large, it's a bad fit for that codebook vector. And in information theory, you ideally want very low distortion values, like very low distances to travel. Like the smaller the distance, the better fit this quantization, this compression is for this paradigm. So what we really found is that by preserving the angle, we get two new behaviors which are not done in the typical straight-through estimator that you get by preserving the direction. The first behavior is that for outward-facing gradients, you're actually going to be pushed away if you have far angular distance from the codebook vector. So if you're a bad fit, then you're going to be pushed towards other codebook vectors, other Voronoi partitions after that gradient update. And that's really sort of indicated by this where the points are sort of moving away in a outward-facing gradient. And this actually increases the information capacity of the compression system when those points hop to other unused codebook vectors. The second case that we observed is for inward-facing gradients, so gradients facing the origin. And in this case, it kind of pulls everything closer towards the codebook vector. So in this case, it's saying all points in my region go closer to where the codebook vector is going to be after a gradient update. So we really see these two behaviors, either this like push factor when you're far away from the codebook vector and there's a gradient which is facing away from the origin, or this pull factor, which is sort of bringing everything closer together. And this contrasts with the straight-through estimator, or just preserving the direction, where all points in the same sort of Voronoi partition, all points that are mapped to the same codebook vector, receive the exact same gradient update. So perhaps it's desirable that, depending on where you are in this region, you get a sort of different update if you're a bad match for this codebook vector versus if you're a good match. If you're a good match, follow the codebook vector. That's what both we're doing and the straight-through estimator is doing. But if you're kind of a bad fit, either get pushed to another region or lock onto this codebook vector and really move a lot closer to it. And we wanted to really evaluate these hypotheses. So what we did was we pulled out a VQ-GAN model from the latent diffusion paper. So they released their model zoo. We pulled down their models. All we did was we switched out the straight-through estimator, preserving the direction with preserving the angle. And all the other parameters are the same. We didn't do any like tricks. We didn't do anything fancy. We just ran all these models from the GitHub repository. And we saw that sort of these two characteristics really show through. So number one is codebook usage. This is the percentage of codes in your codebook that are actually used. We saw this increase drastically. So from 15% to 86%, or from 2% to 27% for these state-of-the-art VQ-GAN models. And we also saw quantization error drop precipitously. This is that distortion value. This is like how close a point is to its actual codebook vector. And these two changes together cause reconstruction FID to drop sometimes by as much as 1/2, and reconstruction inception score to increase as well. We also pulled some video models and just naively tried vector quantization on them. With the straight-through estimator, if you preserve the direction, it falls apart. But if you do the rotation trick, if you preserve the angle, then you actually get pretty good reconstructions. And you might be asking, this sounds really hard. You have to do a rotation. That's not the case. It's really simple. You can just do 2 householder transformations to do it in real time. So it's incredibly fast. All it adds is like 300 products between the encoder output and the codebook vector. So we're not introducing any like new parameters. We're not introducing any hyperparameters, learnable parameters. It is literally just like 3 additional dot products. So I would like to thank my co-authors, especially my advisors, Sebastian, Thrun, and Chris Ray, for helping us drive this project. I'd also like to thank Citadel Securities. I'm currently an unemployed recent Stanford PhD grad, so their support really made coming out to Singapore quite a bit easier because flights and hotels. And finally, I would really like to thank Phil Wang, also known as Lucid Rains. He's a very cracked programmer who has this incredible vector quantization library. And our approach is implemented in his library. We used his to actually develop like a lot of our understanding related to this. So if you actually do want to use the rotation trick, just like use the default vector quantization library that he has. It's turned on by default. Thank you.
Great, thank you. Any questions? Any questions from the audience? Can you use the microphone? Because we are live streaming.
No, it's actually learnable. It's learnable in our case, but we really looked at fixed code books for this. It also seems like the rotation trick does help fixed code books, specifically binary spherical quantization, which figured out a way to do fixed codes on a sphere better than we tried.
Follow-up question. Did you try, instead of following kind of this theory, doing doing something a little different, but we were still preserving the properties of messing with gradients the further they are from the codebook vector.
What do you mean specifically, like different ways of?
Well, I don't necessarily understand. I agree that the rotation itself is valuable, but let's say the further it is from the codebook book vector, then you like somehow randomly mutate it, because that's pretty much what's happening, like as you explained.
Yeah, the hard thing here is how you basically like transform the forward pass. So you don't want to introduce that much overhead to the forward pass. So if you are kind of like, you basically would need a systematic way to map the encoder output to the codebook vector. That gives you that desirable property in the backward pass when you actually differentiate it. So if you have like a different approach for doing this, I'd love to, I guess, chat one-on-one. I'm quite curious what you do have in mind.
Great, thank you. Due to the limitation of time, we only have one question. So thank you, Christopher. Now let's welcome our second speaker, Armin Thomas from Liquid AI. So he will present star synthesis of tailored architecture.